Any of them? Let's take Monday midnight. Mm-hmm.
How many questions?
Not too many. Few.
Yeah, that quiz review.
I didn't
That quiz, that pre-test homework. I didn't open it up till the night before E2, and that was big. So I just got it. That was only.
I told you it has 60 points.
Oh my god. So yeah. I learned my lesson. So we'll expect another big homework assignment before the next midterm, and probably before the final. Well, maybe even before the final. You're nice.
Then how would you know what will be in the final?
Okay, a homework assignment that only covers new material, not a cumulative review of everything over the semester.
I can do that.
Yeah, that sounds fair.
Yeah, our exam also will be cumulative. Mostly every math exam is cumulative.
Yeah.
Mostly. Okay, welcome to another class, guys. How are you guys doing today? Good.
That was a good video. That was an insightful video.
And today we have another one.
Good. Oh, another video. How fun.
Indeed, we have two of them. One is 10 minutes, one is around 4 to 5 minutes. I actually love watching his videos because he explained with the visual.
Yeah.
I love that. Okay, so in our last video, we learned what is vector space. And today we're going to relearn again, revisit them with more information. But before we watch the video, let me give you some background information. Vector spaces consists of vectors. And what is vector? Vector are mathematical objects that have magnitude and direction. Magnitude means length. So it has length and it has direction. And we represent vector with an arrow on the top. And we use vectors are used to model physical quantities like displacement, force, velocity, electromagnetic fields, etc. The key operations in R2 is a vector space, and the key, someone is not. The key operations we do in R2 space is if you take any two vectors, let's say U and V, the components for U is U1, U2, and components for V is V1, V2. Then we say EU and V vectors are equal if U1 equals U2 and V1 equals V2. So basically you take 2 points, X and Y, and let's say we have X1, X2, and Y1, Y2. So not points, two vector X and Y will be equal if X1 equals Y1, X2 equals Y2. Sorry, my bad. X1 equals X2, Y1 equals Y2. And we can add them. So when you add the vectors, you add the components. So X1 plus X2, Y1 plus Y2. We can also subtract them. Means X1 plus Y, X2, X1 minus X2. And minus means it's the same vector, it's the same length, but we just change its direction from going one direction to the other direction. We can also multiply our vector by a constant. It's called scalar multiplication. So when you multiply it by a constant, basically you're multiplying each element in a vector with the constant. And then the last thing we have is norm, which is fancy of saying length. What's the norm of the vector means what's the length of the vector or what's the magnitude of the vector. And in R2, the magnitude or the norm or the length we can find by taking the sum of the squares of each element and then take the square root. So this one is basically if you have a vector here, so you're taking the square of this amount and square of, it's a Pythagorean theorem. So square root, the direct distance, direct length from zero.
Conventional then.
So this is basically saying it's the
All
sum of the
this
x
is
squared plus sum of the y squared.
This does not apply to three. Are we doing three-dimensional vectors?
Not in this class. So there are three types of norm we have. One is L2, which is the Euclidean vector. And in the Euclidean norm, to find the norm, we just take the square root of each element squared. So this equation is same as this one. This is a fancy of writing the same thing. Here it says square of all the elements row wise and column wise. So add all the elements square in row and column, add them, take the square root. So let's say if you have a matrix and you want to find the norm, to find the norm, the L2 norm or the Euclidean norm of this is 1 square plus -7 square plus -2 square plus -3 square, and then take the square root.
Why do you have a 2x2 matrix?
I know this example is, I don't know why they give this example, but vector means only one column. So we can apply the same rule to a matrix also to find the norm. There are also another two types of norm we use, not so often, but we do use them. One is L1 norm and one is L∞ norm. To find L1 norm of a vector of a matrix, all you have to do is you add the absolute value of all the elements. This is L1 norm, absolute value of all the elements. If you have a vector, it's absolute value of all the elements. But if you have a matrix, it's absolute value of all the elements in a column, and then you take the highest number from the column. Whichever column has the highest sum is L1 norm. The other one is the infinity norm. It has two more names. One is max norm and one is sup norm. Sup means supremum. Do you know what is supremum? No. Supremum is like maximum, but it has more criteria, more requirements. So they're not exactly same, but they represent the same thing, maximum, highest one. So to find the infinite norm, you take the highest number in your vector. Yeah, so supremum, we use supremum for a set. And maximum, we can use anywhere.
Max.
So before I give you this example, let's go over this example. If you have a vector means one column, okay? One column or one row. Usually we use column, but here they're using row, but it doesn't matter. The operators are the same. If you have one row or one column, to find L1 norm, you just add the absolute value of each element.
Is that ChatGPT?
AI gave me that. I asked what's the difference between all these norms, and this one is there. But it's talking about one example. For me, I don't have one vector example. I have multiple vectors or matrix example. So that's why in my last class, people are kind of confused. Why you're talking about matrix when you're talking about vector? So first start with vector. If we have vector row-wise, 3, -4, 5, then its L1 norm is 3 plus the absolute value of 4 plus the 5. So basically 3 plus 4 plus 5. So the norm means the length of this vector is 12 in L1 form. If you're talking about L2 form, L2 norm, it means in 2D space, in R2. So in R2, its length is 3 square plus 4 square plus 5 square, and then take the square root. So it's around 7.07. So based on which space you are in, The same thing, same vector may have different length. So in L1 space, we have the length is 12. In L2 space, our vector has 7.
L1 is just a normal triangle, right? That's just the Pythagorean theorem. That's
No, L2. L2 is R2.
So what's L1?
Um,
What kind of shape would that be?
I have no idea. I was trying to find that out, like what is L1 and infinity, but I have no idea. I just know that they are norm. They tell us the length in their space. I have to dig more. Okay, so the last one is supremum or the maximum norm, and it has another name, Chebyshev norm. And to find this norm, it's basically what's the maximum element in your vector, okay, in absolute value. So we had 3, -4, 5. The absolute value is 3, 4, 5. The maximum is 5. So the length, the infinity norm is 5 here. So that's how we do when you have one vector. But we can apply the rule, same rule, in multiple vectors in a matrix. So if you have a matrix, 3, -2, 3 column-wise, -8, 1 column-wise, and you are finding L1 norm. So to find L1 norm, you add them column-wise and look for the maximum number. So in the first column, we have 2, 3. In the second column, we have -8, 1. So when you add them, we have 2 + 3 and -8, we have to take the absolute value. So basically 8 + 1. So 2 + 3 gives us 5, 8 + 1 gives us 9. The maximum of 5 and 9 is 9. So the L1 norm of this matrix is 9. But if you want to find L2 norm, then you do 2 square plus 8 square plus 3 square plus 1 square, and then take the square root. And if you want to find the infinity norm, then you look at them row wise. So row wise, you have 2, -8. The absolute value is 2 + 8. And then the second row is 3, 1, so 3 + 1. So the first row gives us sum 10. The second row gives us sum 4. Our maximum is 10. So the infinity norm gives us the length 10. L1 gives us the norm 9. And the L2 norm gives us something between them, I guess. Okay, Maisha.
What's the difference between the L1 and the L1?
Difference on what you're looking for. So here I have some example given by AI, so I'm not sure how reliable they are. It says, what L1 tell us? L1 is telling us that the distance a taxi would travel to a point, traveling along a grid, as it sums the absolute value of each component. What does that mean? It represents the distance a taxi would travel to a point, traveling along a grid.
You have to add up all the absolute values.
Right. So we have 3, 4, 5. So the sum is 12. So L1 form is 12. So how do we think about it? Probably from going 0 to 3, and then 3 to 4, and then from 4 to 5. How much you get from adding all these distance? Is this what L1 is telling us?
It's like the distance can never be negative, but it's like it's always being added, even if it's going like back, if the type is coming back or going forward, it's always being added. So that's how I understand it.
So 3, let's try plotting. We have 3, 1, 2, 3, and then 1, 2, 3, 4, and 1, 2, 3, 4, 5. So 1 here, 1 here, 1 here. So if you have 3 points, it says traveling along a grid as it sums the absolute value of each component. So basically, you are taking 1 point to the origin, from origin to this point, and then from here to here. Oh, maybe I should draw it in 1D space because L1. So what is the number line? So we have -4. Then we have -3 to -1, 0, 1, 2, 3, 4, 5. So how many units we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. No, I don't know. I don't even know what they mean. Sorry.
Wait, I think maybe, I don't know if I'm not
Mhm.
remember.
It's just
Let's-
along the grid line. What does
Yeah,
that
let's
mean?
say like the taxi starts at 0, right? And then he moves to 3, so he moved 3 spaces, and then he moves to 4, which would be 7. So 3 plus 7 is 10. One of them will be.
Yeah. Oh, the -4 is actually +4 because it's the absolute value. So from 0 to 3 is 3, 0 to 4 is 4, and from 0 to 5 is 5. So you're adding, oh, basically this is what you're doing. If you go from 0 to 1 number at a time, how much you are crossing. So from 0 to 3, you are crossing 3 units. From 0 to 4, you are crossing 4 units. From 0 to 5, you are crossing 5 units. So total, how many units you crossed? 3 plus 4 plus 5, 12. So probably this is what it means, moving along the grid line. But L2 basically means the distance between the point 3, -4, 5 from the origin. And the infinity says the maximum from origin, what's the maximum unit you are going to reach at that point. So the maximum distance from 0 to 3, 4, and 5 is 5, so it's 5 units. Not bad. Somewhere like that. Yeah. Do you remember I could see my linear algebra when I took it? Because I did not understand it very well. So I'm still learning it. Surprisingly, I actually got A- when I took it in graduate level during my MS. So I improved from C to A-, not bad. And right now I'm in the middle. Okay, so one example. Let's say we have two vectors. One is 8, 6, column-wise, and one is 4, -1, column-wise in R2. It says find the length for each vector, and then add the two vectors, find the length of the sum, and then compare the length of the sum with the sum of their length. So let's do this together. And we are in R2, so we are going to find L2. So X1 is 8, 6. So if you are trying to find the norm of X1, what should we write inside the square root? 8 square plus 6 square, which is 64 plus 36, which is 100. And what is square root of 100? 10. So the length from 0 to 86 is 100 units. Now our X2 is 4, -1. So what's the length? Oh, the length of the norm is represented by 2 vertical bar. Double absolute value.
16 plus 1.
So 16 plus 1, which is 17. And do you know how much is square root of 17? So 17 is between which two perfect square numbers?
16.
16 and 25. So if you take the square root of both, what is square root of 16? And what is square root of 25? So can you guess what will be the square root of 17? Close to, I mean, it's between 4 and 5. So 4 point something. 4.1 could be. It could be 4.1, 2, 3, 4, 5, anything. But it has to be between 4 and 5. Somewhere between 4 and 5. Okay, next they are saying, hey, find a new. Go ahead. L2. Because we're in R2. So usually in R2, we use L2. XY plane. So X3, they are saying, make a new vector X3 by adding X1 and X2. Maisha, question? Yeah. If you see R2 means you are in R2 space, means in XY plane. And in the XY plane, to find the distance, we use the
R3 is the 3D plane.
3D plane.
And then
It's vector space. For now, it's vector space. So X3 is X1 plus X2, which is 8, 6 column-wise plus 4, -1 column-wise. So what is our X3?
okay. Okay. X1 is the square root. Are we doing
No, first you have to find the sum. What's the sum of 8, 6 plus 4, -1?
12 and 5?
12, 5 column-wise.
44 and 25.
So X3 is square root of 12 square plus 5 square, which is 144 plus 25. And what is 144 plus 25? 169. And what is square root of 169? 13. So we found the individual length. So this is the
In my timetable.
so this is the norm of the sum, right? It's the norm of the sum. And now they're saying compare this with the sum of the norm. So sum of the norms. What is our first norm? How much is our first norm? X1. What's the norm for X1? 10. And what's the norm for our second one? X2. 4 point something. So what's the sum? 14 point something. So the sum of the norm is 14, while the norm of the sum is 13. So what do you observe? Sum of the norms is greater than norm of the sum. In the exam, I think I'm going to give one this question just for fun. It's easy, right? You're going to find the norms and then compare them. Any question? Now comes vector space. And instead of me explaining what vector space is, I think you should watch a fun video.
Dreamers, darers, story sharers,
and find that our
Hungry Root is the easiest way to eat healthy. Hungry Root is kind of like having your own personal shopper and...
It's Professor Dave. Let's check out some...
I'm going to pray now, so when the commercial comes, please click on the skip button for me, okay?
spaces.
He knows a lot about all kinds of stuff. Professor Dave explains.
We've talked a lot about vectors and matrices lately, as well as how certain mathematical operations like addition and scalar multiplication work on them. Now we want to generalize these operations to define what is known as a vector space, which is sometimes also called a linear space. So let's look at this concept now. Before defining anything, let's just introduce some notation. Let's call our vector space V. If some vector is a member or element of V, we can denote it with this symbol here. So the following means that A is an element of V. All elements of the vector space have the same properties we already discussed for vectors, so elements must abide by the commutative and associative properties of addition, as is shown here. There also exists a zero vector in the vector space such that any element plus the zero vector will just give back the element. For each element A, there exists another element, negative A, within V, such that the addition of the two gives the zero vector. Scalars can be distributed across the addition of two members of V, just as an element can be distributed across the addition of two scalars. The product of two scalars multiplied by an element is the same as one of the scalars times the product of the other scalar and the element. And finally, multiplying by the scalar 1 just gives back that element. So these are simply properties that elements of the vector space must possess. And in this way, we can regard a vector space as a collection of elements that can be added together in any combination and multiplied by scalars in any combination. Now, an important property of a vector space is something called closure. Closure requires two properties. First, for an element A of V, multiplying A by any scalar will give a result that is also within V. Second, for any two elements A and B within V, adding the two elements will also give a result that is contained within V. These closure properties are what determine if V is a vector space. Let's take some time to examine these properties. At this point, it will be useful to introduce this R symbol, which represents the set of all real numbers, meaning positive, negative, rational, irrational, all the real numbers we talked about when we discussed the types of numbers in a previous tutorial. We can pick any element of this set, a real number, and multiply it by any scalar we want. Let's take the number 5 as our element and multiply it by a few scalars. 2 times 5 is 10. 8/3 times 5 is 40/3. 1/9 times 5 is 5/9. Pi times 5 is 5 pi, and so on. Notice that all of our results are still real numbers. This is because no matter what we choose, a real number times a real number is still real. So the set of real numbers satisfies the first closure property. Now for the second property, we will need to choose two elements to add together. We could choose 74 and negative 10, adding them together to get 64. Adding 2 and 4/5 gives us 14/5. No matter what two real numbers we choose, the sum of two real numbers is still real. So because the two criteria have been met, the set of real numbers is closed and can be considered a vector space. Moving to another example, let's expand on our notation. If R is the set of real numbers, Rn is the set of real vectors with a length of some integer n. Similarly, Rm by n is the set of real m by n matrices. First, let's just look at R3 vectors. We can multiply any such vector by any scalar and find that our result is a vector of length 3, made of real numbers. Similarly, we can add any two elements and find the same to be true, given that each component is simply now a sum that will result in another real number. This set is closed and is thus also a vector space. Given what we know about matrix addition, if some set is comprised of matrices with the same dimensions, multiplying by some scalar or adding any two matrices together will not change their dimensions, which makes this too a vector space. So it would seem that vector spaces can actually be made of more than just vectors. In fact, we could define a vector space that was made up of functions if we wanted to. For example, let's take the set of linear polynomials in the form of ax plus b. If we multiply by a scalar c, we can distribute to get ca times x plus bc. Since we are dealing with real numbers, CA and BC will also be real, and the form of our equation is still a linear polynomial, so our result is still within the set. Similarly, if we have two different equations, a1 times x plus b1 and a2 times x plus b2, and we add them, once we group like terms, we get the quantity a1 plus a2 times x plus the quantity b1 plus b2.
I actually use Grammarly all the time to help me write emails to my team. They have pro features too, like sidebars. This allows me to highlight a section of my writing and review several.
Once again, all of these are real numbers, and we get another linear polynomial that is contained in our set. With these two closure properties satisfied, we therefore have a vector space made of functions. We've listed a lot of examples of vector spaces now, so what does it look like when the closure properties are not satisfied? Take, for example, a simple set made of vectors of length 2. However, all the elements of this set have a value of 2 in the second row. Let's take two elements of this set, A and B, and try adding them together. We don't even need to assign values for the entries in the first row to see what will happen. The first row will be the sum of A1 and B1, while the second row will be 2 plus 2, which is 4. Our starting set only contained elements with the value 2 in the second row, but when we added two vectors of this set, we got a 4 in the second row, which means the sum is not a member of the set. Thus, the set is not closed and is not a vector space, despite the fact that it is made of vectors. A lot of the topics we introduce in the coming tutorials will involve working with vector spaces, so let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So you think you know Wix, but do you really? First up, we've got shape video masks. You can use different shapes to create completely different vibes and aesthetics. Or you can create your own graphic. I use the shape composition here. Just import any SVG file and set it as a shape mask. Nice. Next up, we'll keep it moving with the hover box. You can use it to animate any element and create these really eye-catching interactions. And what I love is that the level of control you get here is crazy precise. You can set your animation ease, scale size, and
If anyone's taking discrete, it's the theorem.
There's actually one important one, this one.
Professor Dave here. Let's talk
No,
subspaces.
subspace.
He knows a lot
This
about
is
all
our
kinds
next
of
topic
stuff.
after
Professor Dave explains.
It's all from discrete math.
Once we understand what makes up a vector space, it is fairly easy to understand the concept of subspaces as well. To put it simply, a subspace is a smaller set within a vector space that is itself a vector space. Let's look at some examples to clarify. Let's say that V is a vector space. Now we can highlight this smaller section of V and call it S. Every element of S was already also in our vector space V, so we know they all obey the properties we discussed in the previous tutorial. This means that the only requirement we need to check in order to determine whether S is a vector space is that it satisfies the properties of closure. If S is closed, it will also be a vector space, and because it is completely contained in the larger vector space V, We will then call it a subspace of V. We saw last time that R3, or the set of all real vectors of length 3, was a vector space. So now let's look at a specific choice of vectors contained within R3 and see if it makes up its own vector space, thus qualifying as a subspace of R3. For this example, we will choose a set S made of vectors that have the form x, 0, negative x. By limiting the form of the vector like this, we have chosen a smaller set of R3, while knowing that our chosen set of vectors still follows the rules of the larger set. What we must check now is if our smaller set is closed by checking the two properties of closure. First, let's multiply a vector x by a scalar c. Distributing the scalar c, we end up with a vector cx, 0, negative cx. Notice that this still has the same form that we want for our set, with some value on the first row, 0 for the middle row, and the negative version of the first value in the third row. This vector is therefore still in our set S. Next, let's take two vectors, x and y, both from the set S, and add them together. Provided that we factor the negative sign out of this sum, we will see that the third entry is simply the negative version of the first, and once again, we find a result in the same form as we started. This means that the sum is also contained in our set S. We have verified that S is closed, making it a vector space, and because it was contained within the larger vector space V, this makes S a subspace of V. Before going further, it's important to introduce a few more concepts. Once again, let's say we have a vector space V and a number of elements of V, which we can call V1, V2, all the way to Vn. Any sum of these elements multiplied by some scalars, which we can represent as A1 V1 plus A2 V2 and so on, up to An Vn, is called a linear combination. The set of all possible linear combinations of these elements is called their span. As an example, let's take three vectors from R3, those being 2, 1, negative 1, 0, 2, 2, and negative 1, negative 1, negative 1. The span of these three vectors will be given by the linear combination AV1 plus BV2 plus CV3, where A, B, and C are all scalars. Let's plug in our vectors and distribute the scalars, and then do vector addition to see that the span of these three vectors has the form 2A minus C, A plus 2B minus C, negative A plus 2B minus C. It's worth noting that the span of any number of elements of a vector space V is also a subspace of V. In fact, it is the smallest subspace of V that contains that set of elements, as it is the intersection of all subspaces that contain them. Span will end up playing a significant role when it comes to completely describing vector spaces, but for now, let's check comprehension.
What question you had, Ethan? Okay. So basically what he talked about is that a vector space has two properties. One is closed under addition and another is closed under addition and closed under scalar multiplication. So if you have a vector space and you take any two vectors from the space, add them, the result has to be within your space.
The two properties of closure, scalar multiplication and addition.
Addition. And if you take one vector from the space and multiply by any real number, the result has to be within your space. That's the main idea. And one example of not a vector space is a set where the first element could be any number and the second element has to be 1. So is this set a vector space, is a vector space of R2? So if you take two vectors in from this vector space, let's say the first number is 3 and the second number is 1, and the second vector has the first number 5 and the second element 1. So these two vectors are from this vector space because they satisfy our requirements. What do we have in this set? Now if we add the two vectors, so you get 3 plus 5 and 1 plus 1. 3 plus 5 is 8, it doesn't give us any problem.
Yeah.
But when we add 1 plus 1 is 2.
Then that's not in the set W because.
Exactly, the W requires our second element has to be 1. So this is not a subspace.
So that says that.
If you have a set,
I thought addition, right above it, it says that addition is closed. It's closed under addition, but then, and then you give an example where it is,
so close under addition and close under scalar multiplication, these are the two requirements.
right.
Now if one of them fail to fulfill, then it's not a vector space. So this is an example of what can not be a vector space.
Okay.
So it fails the close under addition property, so it's not a vector space. Maisha.
What does it mean to be closed under addition?
It means if you take any two vectors, add them, the result will be inside your space, the vector space. For example, here one example we have is we have a space with set of numbers where we have the first element in the set is anything, but the second element in the set has to be 1. So it says right now it's a space with all the sets that fulfill this condition. Now we are asking, is this space a vector space? It will be a vector space if you add any two vectors from this space, add them, and it follows the same what do you call outline. The first number is anything, but the second element is always 1.
So when you get a question like this, how do you know what the requirements are? Like,
You have to remember, if you take any two vectors from your vector space or from your space, we always have a space. So if you take any two vectors from your space, the first condition says add two vectors, the result will follow the same requirement as the original space. I shouldn't say requirement, what do you call outline? Same outline as the original space.
how do you know that? Like,
They will give you the outline.
What is that? The outline is you're correct. So like let W equal A.
They will give you the function or the
Is that
formula or anything.
example of an outline?
And then they will ask you. The outline here is first element is anything, second element is 1.
okay.
And then A.
It could be anything, any real number. So this is
What do you
a
call
set.
the second part after the bar? What do you call that?
Oh, how we read it? W is a set of all the elements where the set of all the points where the first element is anything,
second
but the
point.
second element is 1,
Such that.
such that A is a real number.
Okay.
The particle bar means such that or such as those things. Some example of vector space, R2 is a vector space. R3 is a vector space. The number line itself is a vector space. Set of all the continuous function in a closed interval is a vector space. Set of all the polynomial is a vector space.
So R3 is like,
You take any vector from R3, add them, it will be in R3.
wait.
Hmm?
Wait, what's R3?
3D, 3-dimensional.
Yeah.
And if you add two continuous function in a closed interval, it will be continuous.
Taking R3 without.
No, we didn't learn L3, we learned R3.
L3. So there is no L3. It's
Mhm.
stuff out.
Now the subspace, what is subspace? Once you know you have a vector space. So you know you have a vector space, Now you take a small subset of your vector space. And if that small subset fulfill the same requirement as the vector space, then it's a subspace. So a subset of a vector space will be a subspace if it follows the same thing as the original vector space.
But so how do we, I thought we're not doing proofs in this class, how do we?
We're not doing any groups. Instead of grouping, we are looking for three conditions. So a subset will be a
But you have to
subspace.
prove those three conditions for all possibilities, which is essentially a proof.
No, they'll give you a space, a subspace. I mean, they'll give you a subset. And they'll ask, is this a subspace of
Okay.
this space? So in order to be a subspace, first condition is it has to be non-empty. It has to have at least something. So we say, well, 0 is something. So we can have 0 in our space, in the subset. If you have 0 in the subset, then this is your first condition, fulfilled. It's not empty. Second condition is the same as the original one. If you add any two vectors, add them, it has to be inside your space. And if you do scalar multiplication, it has to be inside your space. So if these three conditions fulfilled, then the subset you took from a space is a subspace of the bigger vector space. Confusing, right? Let's do some examples. Let's say we have a set of
Are you trans?
2D elements where we have the condition is that if we add the two elements in your set, the result is always 0. So you're taking a subset from your R2 and
T, what's the T?
transpose.
So why is there no transpose on the right side? What do you
No,
want?
no, no. So this is a vector in row form.
Oh, T, okay. And then you
So
take the
we
transpose
have a
back.
column vector x1, x2. But they didn't write it as a column vector. So probably to save space. I mean, I did to save space here. But it's from the book. So probably they also did to save space. So it means we have a column vector x1, x2. In R2, it means in 2D. In xy plane, we have a vector x1, x2. Now, this set has one condition. If we add your x1 and x2, the sum will always give you 0. Is this a subspace of your bigger 2D plane, xy, R2? Yes.
Okay.
So you have to see the three conditions. First condition, this set cannot be empty. It means we have to have at least 0 vector in it. So do we have 0 vector in it? Let's say our first component is 0, second component is 0. So if you add the two zeros, what do you get?
0,
0.
0.
So the first, for 0, our condition is fulfilled, is satisfied. 0 vector is inside this set. Now the second condition says, if you add any two vectors, then again, their sum has to give you 0. So let's say you take one vector u and another vector v from this set. That means u has this condition. u1 plus u2 is 0 and v1 plus v2 is 0 because you took it from the set. So whatever condition the set has, your two vectors will have the same conditions. So u1 plus u2 is 0, v1 plus v2 is 0. Now, what if you add u and v together? If the sum is 0, then it will be closed under addition. So let's add u and v. u is u1, u2, v is v1, v2. So if you add them, it means u1 plus v1, u2 plus v2. So these are new vectors. u1 plus v1, u2 plus v2. Now this set says, if we add the two components in a matrix, the sum is 0. So let's say if we add the two components, e1, v1 plus e2, v2, then you get e1 plus e2 is 0. V1 plus V2 is also 0. So the sum is 0. Maisha.
Would you do U1 plus V1 and U2 plus V2?
Right. And the set is saying you add the two components and add them.
So then what do you mean when you say, U1, U2 is 0 and U1?
So you are adding E1 plus V1 and U2 plus V2, right?
Okay.
So adding all four together. So for convenience, you can put E1 and U2 next to one another, V1 and V2 next to one another.
Also, you can add the, I see.
You're adding the components and the result will give you 0. So when you add the components, E1, U2 has to give us 0 because this is from the set. V1 and V2 has to give you 0 because this is also from the set. So 0 plus 0 is 0.
So we can take any two vectors. from
Any two vector. That's why we don't put number with variable, like E1, U2. We don't use 1, 2, 3, 4 like that.
Okay.
Okay, so it's not empty and it's closed under addition. Now the last condition is it closed under scalar multiplication? So you take a vector V, which has V1, V2, and you multiply by a constant C. So we get CV1 and CV2. These are the two components in the scalar multiplication. Now the set says add your components and the result has to be 0. So CV1 plus CV2. You see they both have C in common. So factor out C, you get C times V1 plus V2. But what is V1 plus V2? It's 0 because this is from the set. The set says the components in a vector, the sum will give you 0. So basically your C times 0, which is 0. So when you added two vectors, you get the result 0. When you multiply by constant, you get the result 0. And this is not an empty set. So is this a subspace of R2?
Yes.
Yes.
So can you conceive 0?
Any non-zero number. 0 is a cheating number. Like with 0, you can do anything. Go ahead.
So is that kind of inside of the set that we're talking about, the only element is 0?
No, the set you're talking about has the property, if you add the two elements, the sum is 0. So any set with two elements, if we add the two numbers, the result is 0. This is the set we have here. And we took it from R2. R2 means the XY plane.
And it's not like a specific, like, do those variables like represent a specific number, or they're just like variables?
They represent all real number. So all real number that satisfy this condition. The sum of two numbers is 0. So what type of number actually satisfy this condition? Exactly. Two numbers that are the same number that has opposite sign. So this is basically consists of 1, -1, 2, -2, 3, -2, 3, -3, 4, -4. So it's set of all the numbers like that.
Well, what about like -1, negative?
It doesn't matter what number you take, the sum has to be 0. So the only way you can have the sum 0 is the same number is opposite sign. Actually, it's not true. Is it true?
No, really, like, wait a minute, no.
I mean, it is.
It's not true, it's not true. It's not true. It has to be the same number, but just positive, negative, and same number. Can't be.
Yeah. We cannot have two different numbers, but the sum is 0.
You're gonna have like a 40-60 split. Right. Yeah, it has to be 50-50, which is 50-50 is the same number. Yeah.
Exactly, same number.
Yeah, not totally.
Yeah, 0, same number, yeah. 0 and every number else, everything else with same sign. I mean, same number with different signs. The next set, we have a next set. The next set is consists of all the numbers x, y, such that their squares are same. The number could be different, but their squares are same. Is this a subspace of R2?
Condition 1 passes, 0 squared is equal to 0 squared.
Mm-hmm.
Condition 2, it must be close under vector condition.
Mm-hmm.
Uh,
That means you have to take two vectors from this space, from this set, add them, and see if their squares are the same thing.
oh yeah.
Try it. It's a
Oh,
fun
two.
one.
Wait, so 2. So over 2 that's
So you add them with 2 column matrices?
Yeah, but the condition for those columns are their squares has to be same. The numbers themselves may not be same, but when you square them, they are the same number.
oh, so it could be, wait, x1 could be 2 and x2 could be 3.
So you found a counterexample that fails.
Yeah.
So if you found a counterexample, then you use proof by counterexample.
So it
Proof
is-
by contradiction. It is not a subspace.
This guy's about right.
It's not empty, it has 0, but it's not closed under addition. What counterexample you have, Ethan?
2 negative 2. Or no, sorry, 2 3.
But you have to have, so E1. You have to have 2 elements. What 2 elements do you have for E1?
Oh,
The condition says their squares are same.
but it's 2 2 by 2 2 by 1 matrices. So it's like a negative 4 and a 4.
Good. So 4, negative 4. They are not same, but their squares are same. I know, somebody, probably I should not. I should do that.
So what if we did 3 negative 3?
And then we have 3, negative 3. So let's add them. What is E1 and E2?
Wait, yeah, that doesn't work at all.
No, not 0.
Oh, yeah, yeah.
It's not 0. You have 4, negative 4, 3, negative 3. So we have 7, negative 7.
Let's change 3 negative 2. Don't break it.
No, does it work really?
It does, yeah, you square negative
3
7.
plus,
Same thing as positive 7. Right? It's
oh yeah.
not put that in there. Just change negative 3 to negative 2.
You cannot,
Oh, what's this?
because their squares has to be same.
Oh, so this works. Works. Every number works.
Is it?
Yes, there you go. You square a negative number, you get
Counter example. How about 1, 1 and 2, negative 2?
it.
1, 1 and 2, negative 2.
So wait, what's the condition for the both numbers in one variable, like x?
No, the condition in this polynomial, not polynomial, in this set is that their sum has to be same. So the square has to be same. So the individual numbers may or may not be
So it could
same,
be the
but
same
their
number.
squares has to be same.
Oh, okay, 1 1 works. Like 2 negative 2 works.
And if you add down,
That's-
we taking attendance. Today is what, 29?
Like, where did you see that you can?
It says their square has to be same. It didn't say anything about the individual numbers. So we have the same number or we have the same number with different signs. How about the next one? The next one is interesting one. It says you have 3 elements. So you are now in 3D space. Your matrix, your vector has 3 elements. The sum of the first 2 elements is the third one. Sum of the first element will give you the third element. Is this a subspace of R3? Think. Park, here. Jose, here. Mehrab, Sikh, Kenyon, here. Bora, here. Andy, here. Because it's a different class, Maisha. Chuyan, not here. Jackson, here. Christian is absent. Emmanuel, here. Gregory, here. Abid, absent. Orji, absent. Vlad, absent. Ethan here. Elsa here. What happened to all these people, guys? 1, 2, 3, 4, 5, 6. I know 2 of them, they're sick. But how about the rest? If you guys are watching this recording, let me just remind you, attendance is 5% of the grade. Okay? So attendance is not free, it's 5% of the grade. And if you're absent, that means you're losing 5% from 100%. So you're losing your A. Especially if your exam score is bad. And your homework score is also not so good. Okay, so what do you think? Let's check the first condition. No, you cannot do anything. It's the condition.
Yeah, but
You have a vector consists of 3 elements. You have a vector consists of 3 elements. The third vector is the sum of the first 2 numbers. Sum of the first 2 elements. So condition number 1, is it empty or non-empty? So you're looking for the 0 vector. So is 0 inside your S? Yeah, because 0 tells us that it's non-empty.
So you have your own.
1, you're not sure, but as long as you have 0, you have something in there.
How would it,
So for 0 vector, you have 0 and 0, the first 2 elements. And what's the third element? 0 plus 0? 0. So we have 0, 0, 0. So it's satisfied our condition.
so, like could it have like multiple conditions, like
No, it has only one condition. The sum of the first 2 is third one. The first one and the second one could be anything. But the sum has to give us the third one.
Yeah, but I'm saying like not in this example, like in a different example, could it have like multiple conditions that satisfy? Yes.
It's up to you if you want to have that.
Yeah, this for that. Okay.
Now let's check the second condition. Is it closed under addition?
Separated.
So we take 2 vectors from this set. Let's say the first vector is U, which has U1 and U2. The first 2, we don't know what the numbers are, but what the third element must be. U1 plus U2. And let's take another vector V. V1, V2. What's the third element? V1 plus V2. Now if you add them,
U1 plus
U plus V. So U1 plus V1, U2 plus V2,
U1 plus B1 plus U2 plus.
V2. So we have to check if we add these 2, does it give you this? I mean, really? Yeah. So U1 plus V1 plus U2 plus V2, is it same as U1 plus V1 plus U2 plus V2? It's the same. Yeah. The second condition is satisfied. It sounds weird, right? But yeah, they're same.
When do you get the second U1 first? Like the second one first?
So you're adding U and V. The first element in U is E1, the first element is V is V1. So when you add them, it's E1, V1, E1 plus V1. And then the second element is U2 and V2. So U2 plus V2. And the third element in both metrics, the third element is U1, U2 and V1, V2. So if you add them, it's U1, V1, U2, V2. So they're same. So satisfied. Now the third one. So C times U. So C U1, C U2, and C U1 plus U2. So this is same as C times E1, E2, and U1 plus U2. So it also satisfies, right? Satisfied. So since all three conditions satisfied, so yes, this is a subspace of R3. And that's how you have to check individually, one by one. If you think it's not a subspace, just find a counterexample and you'll be fine. You don't have to disprove by all the work. You can disprove by counterexample. We don't have time. So we're going to have more fun in our next class, okay? With more examples. I love teaching this section actually. You guys are more energetic than my other class. My other class are all grumpy people. Yeah, but see, you're having more fun here. So have a good night, everyone. See you on Monday. He left. But you can meet him in next class again.
I was gonna ask him for his, because he's also in computer science.
Oh, he came back.
He did. He was here. Lincoln?
What?
You have Lincoln?
No. I did not.
Oh, because you'll be really helpful, because you're ahead of me in computer science.
Where are you? Oh, when are you? Oh, where are you?
Monday I'll be here around 4:30.
4:30. Okay.
So come here Monday, okay?
That's up to one of my